Hi, Assalamualaikum and very good day. Welcome back to my session for chapter 4. So today we're going to continue chapter 4 in part 3. Okay, so we already finished part 2 in which that we learn about radiation from surrounding to small object. Alright, so now in part 3 we will cover about combined radiation and convection. Okay, so basically what is combined radiation and convection? So this concept is actually derived from these fundamentals in which that we measure what is the net heat between the convection plus radiation which is occur at the same time. Okay, so by referring to this equation here, okay, uh, well, this is the convection plus radiation, where convection represents by this equation and radiation by this equation. And if you notice here, the temperature difference for both equation is the same. So therefore, we can actually rewrite or rephrase the equation into this form, okay, where the terms here is actually put it together like this, okay, and the HC and HR here is placed like this, and the area involved is actually the area of the surface or object. And if you notice here, A here, and we have A1 and T1. So T1 here is actually temperature of the reference point. Okay, so same goes to the A here, is also temperature of the the area of the reference point or reference object. Okay, so in order to explain in detail about the HC, the coefficient for convection and coefficient for the radiation, I will explain it later in the next slide. Okay, let's begin with the HC. How can we determine the HC? So for your information, the convection part in this equation is only refer for the convection types considered as a natural convection only. We're not going to consider the forced convection in combined radiation plus convection. We only consider natural convection, where under natural convection we only have two possible mechanisms, whether it is categorized as natural convection from planes and cylinder, and the other one is natural convection in enclosed space. Okay, so let's begin with the natural convection from planes and cylinders. Okay, so this one is very straightforward. You have to use this table. In order to use this table, we should determine first the range. We should identify first what sorts of physical geometry of the objects. Okay, whether it is vertical planes or cylinder or horizontal or any other characteristic, we have to identify first. Once we already distinguish which category it falls, and then we should calculate the Grashof times NPR. Therefore, we can use the correct equation to determine the H values here, and this H value is actually the HC that we are looking for to substitute into this equation. Okay, and as I mentioned before, there's another category of natural convection which is called as an enclosed space. So the best example to explain about the natural convection in enclosed space is like a double glazed window. So in double glazed window, we have two layer of window, which is it is separated. This is a window 1 and this is a glass 1 and glass 2. Okay, and this window is actually separated by an air gap here. Okay, so that's why it's called enclosed space. And in fact, the gap here is actually symbol as sigma. Okay, so in order to use this equation, we have to identify first what sorts of liquid which is filled up in this area, in the gap here, whether it is liquid or gas. If it's gas, then you have to use the list of equation here. If it's liquid, then you have to use the equation list down here. But again, both types of fluid, you have to determine what sorts of the range of Grashof times MPR number. And what I can summarize here, in both type of mechanism, we should know first what is the range of Grashof times MPR number to use the correct, to determine the correct formula to determine the HC. Okay.
Beats music.
Okay, let's proceed with the HR term, which is the radiation coefficient. Okay, so basically in order to determine the HR, there are two equation that we can use, whether this one or the other one here. So what's the difference between this one? Okay, well, if you look at it carefully, the difference is on the term of Stephen Boltzmann here. If we refer to the first one, okay, the terms of Stephen Boltzmann here, okay, it didn't include the 10 to the power of minus 8 here. Okay, it's just include the number 51676, and the other difference is this one also has the temperature need to divide by 100 for the upper part here, and that's the reason why the 51676 here didn't have the terms of 10 to the power of minus 8 here. Okay, well, the other one, for the other equation here, okay, if you use this one, you have to use the full equation for Stephen Boltzmann number here. Okay, that's mean 5.676 times 10 to the power of minus 8. Okay, the term here must be used the full terms of Stephen Boltzmann constant. Okay, and in fact if you look at the temperature here, you don't need to divide by 100. It's just the temperature itself. Okay, which is different to this term where you have to divide by 100. Okay, that's the only difference for HR. Okay, this is the main equation to determine the heat transfer due to the combined convection and radiation. Okay. However, the terms of HR here, which is also consists T1 and T2 term. Okay. So that's why in order to avoid confusion with the T1 and T2 term consists in HR parameter, with the terms of T1 and T2 consist in the main equation, I strongly suggest that we replace the T1 and T2 term in HR with this term. Okay, so we just stick that the T1 should be the highest temperature and the T2 should be the lower temperature in order to determine the HR. Okay, so this is actually the equation that I've shown you before, where we still have the T1 and T2. Okay, or you can use the other equation. Okay, however, as I mentioned before, we want to avoid confusion. So in HR equation, to determine the HR, okay, we're supposed to replace the T1 and T2 with the high and low temperature term, like this, or either like this. However, for T1 and T2 term in the main equation here is based on the equation, which one as a reference point. So the reference point should be, the reference object temperature should be T1. Okay, and the other object is T2. Alright. Okay, let's do example 1. And the question is given here, where the small oxidized horizontal metal tube with the dimension is given here, and the temperature of the temperature of the metal tube is 588, and this metal tube actually is placed in a furnace where the surrounding temperature inside the furnace is 1088, and the emissivity value also given at different temperature. Okay, so the question asks you to determine what is the Q by considering combined convection and radiation. And if I can simplify the diagram, is look like this. So actually this is the same question that we did in part 2, in a case where the radiation from surrounding to a smaller object. The only difference is, in this case, we consider that there is a combined convection plus radiation. So how can we determine the Q in this case? By considering both mechanisms at the same time. So since the question is related to the combined convection and radiation, so therefore this is the equation that we're going to use. So if you notice, the coefficient here, we use two types of coefficient, which is Hc and Hr for radiation. So let's begin with the Hc. Hc in this case, because it is in the category of metal tube, so we can use this formula of Hc here. Okay, but how do we get this formula for Hc? Actually, it is again referred to the table 472 that I showed you just now, where the range of the Grashof times MPR should be determined first in order to determine which equation are suitable to be used. Okay, and the formula for Grashof number is given there, and if you notice that these terms in the Grashof number is actually labeled as alpha, can directly get from the tables. Okay, the only things that you need to substitute is actually this term here and the term of delta T, and multiply with the terms of alpha, then you will get the Grashof number easily, rather than calculate one by one. And now let's look at the HR value. HR, you can either use this formula or the other one, which is you have to use the full terms of Stephen-Boltzmann constant. Okay, but in this case I just choose use this term. Okay, so we got the HR equals to 487.3 and HC at 15.64. Area. Okay, so since the shape of the tube is in a cylinder form, okay, so we use this surface area formula pi dl, and T1, in this case T1 is actually the tube itself as a reference point, so that's why it is 588, the temperature of the tube, and the T2 is actually temperature of the furnace. Right, so since we already calculate all the parameters needed in the equation, especially on Hc and Hr, then finally we can substitute into this main equation. Okay, and again I would like to remind you, in this case always make the lower temperature as the reference point, in this case the T1, which is the metal tube itself, the horizontal metal tube. Okay, so that's the reason why our Q value in this case is negative. This is because our reference point in this case, which is the metal tube, has a lower temperature compared to the surrounding. And I also mentioned in a previous lesson in which that when the Q is negative, that's mean the object receive the heat. So in this case, the metal tube receive the heat from surrounding, okay, due to the convection and radiation. Alright, that's it. Okay, let's do a bit difficult question, okay, compared to the one that we did before. Okay, so in this case, the question stated that a double glazed window is constructed by two layer of glass. Okay, so it will look like this, double layer, okay, where the glass is separate by an air gap with a thickness of 5 cm. So there's a gap between the first and the second layer here, which is 5 cm. And the dimension is given, which is, this is the height of the window, 2 meter, and the width is actually 3 meters. So this is the white area, the white region, okay. So from question A, it stated that it is assumed that the surface temperature of the glass between the air gap are 15 degrees C and 5 degrees C. Well, it's actually look like this, but I can provide you simpler diagram. Okay, so it says that the surface temperature on one layer is 15 and the other layer is 5 degrees C, and it is separate by 5 cm. Okay, so determine the Q, okay, by considering the natural convection and radiation. So we know that in this case, the Q that we're supposed to use is the Q which is consists of H C plus H R. Why? Because the equation mentioned here is heat transfer involved by natural convection and radiation. So when there are two mechanisms occur at the same time, so you have to use this one times with A T1 minus T2. Okay, so what about equation B? For equation B, it stated that if the glass with 5 degrees Celsius is broken, so now the window become only one layer of glass, and it is assumed that the outside temperature is 3 degrees C. So again, determine the Q due to the combined convection and radiation. So it will become like this, okay, where since the 5 degrees C now, since the window with the 5 degrees C is broken, so the temperature inside maintain 15, but here it is 3 cm since the window is broken. Okay, and the dimension of the window still the same, didn't change anything. Okay, so let's solve this question. Okay, let's start with question A, in which we want to determine the Q due to convection and radiation. So let's start with the coefficient of Hc, which is the convection coefficient. Well, in this case, we have the double glazed window. So as we have the double glazed window, so it is categorized as the natural convection in enclosed space, because there is a gap between the window, okay, the glass, so, and here there's an air gap, so that's why we call it as a natural convection in an enclosed space. So we have a list of equation here, so therefore we should know first what is the correct range of Grashoff's time NPR number. So in order to determine the NPR number is not a problem, because we can just get it from the table. But for Grashoff number, we have used this equation. Well, to use this equation, there's a trick on that, in which that the items that I circle here, which I label as alpha, which is including rho, g, beta, and mu here, I label it as alpha because this item actually we can get it directly from the table. Okay, so for example here, this is the properties of a table. Okay, so these are the items that I label as alpha, in which that you can get from the last column here. So in order to determine the Grashoff number, you just need to multiply with the here is actually the space of the gap, okay, which is In this case is in this equation is 5 cm, okay, and delta t is the difference between the two surface of the glass window. Okay, so that's it, very straightforward in order to determine the right equation. Okay, so after you know what is the Grashof times NPR number, so you have to check on the range here which equation that you should use. Okay, now let's move on the HR, which is the heat transfer coefficient in radiation. And this one very direct. You just use this equation, and remember for T1 I always use the temperature which is at the higher temperature, okay, and the T2 is for lower temperature. Okay, and A1, since this is the area of the glazed window, double glazed window, so the area is, the dimension is given, so we can just get it directly. And T1, so in this case I use T1 as 15 degrees C, which is the higher temperature, and T2 as the 5 degrees C. So why in this case I use T1 as the higher temperature? Because in this case I want to choose the room as my reference point. So imagine that if we have the double glazed window, okay, so the temperature here is actually 15 and temperatures here is actually 5 degrees C. Okay, so in this case I want to use the room itself. This is the room and this is outside. Okay, outside. So in this case I want to choose the room as my reference point. So when I want to choose the room as my reference point, I know that the when we solve this part, okay, we know that we will get the positive value for the temperature difference here. Therefore we consider that the room is actually released the heat to the surrounding. Okay, let's take a look at the solution. So from the input information from the equation, we have a temperature of surface T1, the surface of the window T1 and T2, okay, and also the emissivity, and in fact the dimension also given, okay, and the length here is actually the refer to the space between double glazed windows. So for example, this is the first and the second window, okay, so this is actually the space which is given in the equation. Okay, well, from that we have to determine the TF in order to get the properties of air, where all the properties must be evaluated at TF. Okay, and the TF here is actually different to delta T, as you know that delta T is only the difference between T1 and T2, but the TF here is actually refer to the to this formula. Okay, I just want to remind you that the TF properties is actually very important to determine all the properties of the air in order to calculate the Grashof and NPR number. Okay, so that's why we need to calculate the TF number first. Okay, so since we already know the TF number in this case, which is 10, then we can directly get the items, or which is I label before here as alpha, where the alpha term is needed in the equation here to calculate the Grashof number. Okay, so again the alpha term is actually at the last column. So in order to calculate the Grashof number, you just have to multiply with the length here is actually the distance between the gap, okay, and this is the temperature difference. Okay, and after we get the Grashof number and also the NPR from the table, and then we can get the number which is the Grashof times NPR number. This is very important parameter, where this parameter will be used to get the correct range of the formula to calculate the HC in this case. Okay, so based on this number and also the table that I show you before, okay, so the Grashof number is lies between this range. So we can use this formula. Okay, once we already know the correct formula to calculate the HC, okay, which is this the formula, so we can directly calculate the value of HC. Well, I want to remind you here, especially on the part of sigma here. Sigma here is actually refer to the space gap between the double glazed window, between the enclosed space. So in this question it is 5 cm. Okay, and the length here is actually the length of the window. Okay, so don't get confused with the length and the space here, the sigma here. Okay, so this is actually the NU term. So from the NU term, okay, we can get the H term here, which is represent the HC term in this case. Okay, well, this is the properties that we can use in order to calculate the HC number. Okay, and lastly, after we already finished the HC, now we can calculate the HR. So remember the HR, we can just simply use this equation. Okay, and for Q, okay, we can use this final equation to get the Q due to the convection and radiation. Remember, in this case, our T1 is actually the temperature of the room side, okay, which is 15. Okay, and the T2 is actually temperature of the window on the outside part, okay, on the outside layer, which is 5 degrees C. Okay, so finally we managed to calculate the Q. Okay, for question B, you have to do it by your own, but don't worry, I will give you some guideline how to complete the task. Well, you're still using this equation because we still consider it is combined convection and radiation. However, it's no longer double glazed window because one of the layer of the glass is broken. So it's become like this, and even the temperature here is becomes 3 degrees C, okay, instead of 5 degrees C as part A. Okay, so as usual, let's start with the determine the coefficient for HC and HR. So we start with the HC first. Okay, so for HC, we have to really understand what sort of mechanism of convection happen here. Okay, it's no longer natural conversion in enclosed space because there's no enclosed space anymore. So it is actually considered as natural convection from various surface. Okay, and in this case, we consider as it is a vertical planes because the window here, okay, the glass here is in vertical direction and the glass is considered as a planes. Okay, so this is the range that we are supposed to use. Okay, so now check it with the range of Grashof times NPR number, and this one is the same as well. You just have to calculate the Grashof number. Remember the step that I showed to you in which that we can just get the alpha term from the table. Okay, use that step. Okay, so I'm not going to show it again because I already showed you before. Okay, now let's proceed with the HR. Again, the HR also the same procedure. We just have to substitute in this formula. Remember, for this one, always use the higher temperature as a T1. Okay, and the lower temperature for T2. Similar as well to the item at the bottom here. Okay, and lastly the area. I bet the area is still the same. Okay, T1 and T2 still the same. Okay, so good luck. Okay, so we already complete the chapter 4. Okay, if you have any question or any doubts, okay, you can raise the question during the forum session. Right, see you again.